So for this first question, I'm going to break up my first term here. 2 to the power of n plus 1 becomes 2 to the power of n times 2 to the power of 1. So there I'm basically using the first law of exponents that says if you multiply things that have the same base, then you are permitted to add the exponents. Okay, and I'm just reversing that law. And I'm going to do the same thing here. 8 times 2 to the power of n minus 3. I'll change it to 2 to the power of n times 2 to the power of 3. And I like to put this dot actually a bit higher up, like over there. Right, and at the bottom, we'll do the same thing. Now, and just so by the way, the reason I put the dot a bit higher up is so that it differentiates between like the decimal sign and the multiplication sign. So that dot implies that we are multiplying these two things. And I don't want you to think this is like 8.2, you know, like the decimal 8,2. So yeah. Okay, then I'm going to take out my common factor here. Let's have a look. 2 to the power of n, and here we have another 2 to the power of n. I'm taking that out as a common factor. That leaves me then with, so if I remove the 2 to the power of n's, that leaves me with 2 to the power of 1 minus 2, actually, here's an 8 first, minus 8, and 8 is being multiplied by 2 to the power of negative 3. So we have 2 to the power of 1, which is just 2. Let's move that over here. And then you have 8 multiplied by 2 to the power of negative 3. Which actually I should have also simplified, but I'll do it in the next line. And this 2 to the power of negative 2, I'll change it to a quarter. Okay. So I'm going to copy everything the same, but 2 to the power of negative 3 is going to become 1 over 8, because 2 to the power of 3 is 8. And so negative 3, or 2 to the power of negative 3, we just inverse that and make it 1 over 8. These things cancel. We get rid of our 2 to the power of n's, because you're dividing them by each other. On top, you have 2 minus 8 times 1 over 8. These two things also cancel, and that leaves us with 1. At the bottom, you have a quarter. Now, 2 minus 1, can I just move up? 2 minus 1 is just 1. But instead of dividing by a quarter like this, what I'm going to do is I'll change that to 1 times the inverse of a quarter, which is 4 over 1. And that means my answer is 4. Okay, all right. So moving on now to question 2.2. We have equations like the x root of 27. I actually don't know how you pronounce this. So I'm just saying the x root of 27. And it's equal to 2,187. Okay. The goal is to solve x. Okay. So you want to start off this problem by writing the 27 as 3 to the power of 3. Okay. And then the cube root, or not the cube root, sorry, but this root x of 3 to the power of 3, that can be rewritten as 3 to the power of 3 over x, right? So this index that you have there outside the root is what you use as your divisor for this exponent. Okay, then 2,187 is going to be broken up into 3 to the power of 7. And now that your bases are the same, you can make your exponents equal, okay? The moment you've reached this point, that your bases are the same, you can now equate your exponents. Okay, and to solve this part is now going to be straightforward. I'll just do it over here. We're going to cross multiply. Let's rewrite it as 7 over 1. Multiply the 7 with the x and the 3 with the 1. So that's 7x equal to 3. Divide both sides by 7 to get x alone. And here's your final answer. Yeah, so you can always double check your answer by substituting it in. Here we're going to put that fraction. What was the fraction now again? 3 over 7. And then here we put in the number 27. And yeah, it's equal to 2,187. Question number 2.2.2. Here we have 4 to the power of x minus 16, and it's equal to 6 times 2 to the power of x. So with this one, it's important to figure out what you want to do for this question, right? And I can already see here that when I break up the 4 into 2 to the power of 2, okay? And let me just rewrite everything as is. Kind of just giving you my thought process here. Even if I decide to let's say take this term over to the other side and have everything here on the one side equal to 0, then I won't be able to take out a common factor. Like 2 to the power of x, I won't be able to take that out as a common factor because, first of all, this term doesn't have 2 to the power of x, but also, if let's say I had the 16 on the other side, I would still be left with another 2 to the power of x, because this is essentially, this term here is essentially 2 to the power of x squared. So instead of thinking of it as like taking out a common factor, rather think of it as a quadratic equation. So this is what I'm going to do. I'm going to say let 2 to the power of x be equal to k. And then this 2 to the power of x simply becomes k. So that's going to be 6 times k, or I can just say 6k. This will be 16. And remember, we said this is like 2 to the power of x squared. So that's going to be k squared, right? Forming my quadratic equation here, k squared. All right, let's bring all the terms to the one side of the equation. And now we're just going to factor from there. Okay, let's scroll down. So this is where you want to be. Factoring this expression, we get the factors of k. Negative 16 can be broken up into 8 times 2, or negative 8 times positive 2. Notice they also add up to this middle term. Okay, therefore, k is either equal to 8 or k is equal to negative 2. Okay, now let's substitute k for this expression that we got in the beginning. Remember, we said 2 to the power of x is equal to k. And if k is equal to 8, then 2 to the power of x is also equal to 8. So we can solve that further. Let's go ahead. 8 can be written as 2 to the power of 3. Therefore, x is equal to 3. Right? Remember, we had another solution. So let's start there. 2 to the power of x is equal to negative 2. But if you have some exponential, right, some expression to the power of this exponent, a base to the power of this exponent, it's never going to be equal to a negative number, right? any exponential graph would always be greater than 0. Okay, so 2 to the power of x is never going to be less than 0. It's never going to be negative, which means we have no solution for x. Okay, it's impossible for us to solve that equation because exponentials will never be negative. Even if the exponents were negative, the numbers just become really, really, really small and become so close to 0, but it will never be equal to 0 or anything less than 0. So, question 2.1.2. How do we tackle this one? You have a square root here. It's being multiplied by another square root. Now, let me just tell you that if you were multiplying, let's say, the square root of a by the square root of b, then that is simply equal to the square root of a times b. An example of this might be if you have the square root of 2 times the square root of 3, then this is equal to the square root of 2 times 3, which is the square root of 6. Okay, so I want to do that now, and I want to multiply those two square roots with each other. So let's put it all over the same square root. I'll take whatever is inside this square root. Sorry, let me do that again. Whatever is inside this square root, and I'm multiplying it by whatever is inside that square root. Okay. The next thing I notice here is the fact that these brackets that I'm multiplying inside the square root looks very similar to each other, almost identical. The only difference is that this one has a plus, that one has a minus. Now that rings another bell in my head. I know that if I multiply expressions that look the same, two binomials that look the same, the only difference is the one has a plus, the other one has minus, then that ends up in difference of squares, meaning it's the first term squared minus the second term squared. So I'm using that shortcut now. I'm just going to square the first term, and I'll subtract it by the next term squared. So my first term in this bracket is x. So we square that. And then we subtract it by the second term in the bracket, which is the square root. But remember, if you square a square root, then the root just falls away. So we are then just left with the 2x minus 1, and the root falls away. Okay. I'm going to simplify what I have there by distributing the negative into the bracket. So that gives me minus 2x plus 1. And immediately I notice or recognize that as a trinomial, which is factorable. So the factors of this trinomial will be x minus 1 multiplied by x minus 1. And that's a perfect square. Something multiplied by itself is a perfect square. So you might write it as x minus 1 to the power of 2, right? When something is being multiplied by itself, you can just write it as that thing to the power of 2. But now this square cancels the square root, or let me rather say the square root cancels the square. And it leaves us now with just x minus 1.